Hello, my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on inorganic chemistry and the periodic table. This is for the developing metals topic, and there's two videos in this topic that cover the DM topic, and it's for OCR B salters. So this video actually goes through the specific content for salters. So if you are studying salters at A-level chemistry or A-level chemistry salters, then this video is perfect for you. It's not generic, it's actually tailored towards the specification. And in fact, there's a full range of salters videos. There's year 1 and year 2 videos, all on Allery Chemistry YouTube channel. I've also got some generic whiteboard tutorials as well, where we go through some specific topics which are quite generic, but there's a full range of stuff on there. It's all for free. All I ask is you hit the subscribe button, and that'll be absolutely fantastic. This video here is actually created from revision slides that I've made, and they're available to purchase. So if you'd like your own copy of these, if you click on the link in the description box below, they're great value for money. You can use them on the move, on your smartphone or on your tablet. I've known people to print these out as well and use them as revision notes, for their own use, and put it in their files. So you can get the full range for year 1 and year 2 salters, all available on that link. So just go and have a look on there. Okay, so like I say, this is dedicated to salters for the developing metals topic. There's 2 videos in this series that covers DM, so I've decided to split it up because otherwise it would be a very, very long video if it was all in one go. So this video is going to cover areas such as transition metals. We're going to look at that. We're going to look at what ligands are. We're going to look at d orbital splitting. We're going to be looking at complexes, and we're going to look at some colours as well, so reactions of that, including ligand substitution. And then finally, we're going to look at some coloured complexes and how we can analyse them and determine the metals that's in solution. So that's the running order for this video. So we're going to start by looking at D block elements first. So you need to know where the D block elements are in the periodic table. So you can see there that we've got the periodic table put in front of us, and the D block elements is this middle bit here that's highlighted in red. So it's this bit here. Okay, so these are your D block elements. So some of these elements are transition elements, not all of them though. You must distinguish the difference between a D block element and a transition element, and we'll look at that a little bit later. So the ones that you mainly need to know, the ones in the top row of the D block there, so that's scandium, which is Sc, through to, you've got titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. So you just need to know mainly these ones here, and the video is really going to focus on that. But you may be asked some of these, but it's mainly you need to be quite knowledgeable on these ones here, and you'll be doing just fine if you can do that. Okay, so we're going to look at the electron configuration. So we know where these D block elements are, so we need to know why they're called D block elements first, and what the difference is between that and transition elements. So the electron configuration is actually quite important, and you would have seen this in year 1 chemistry. So this is just using some of the knowledge from year 1 chemistry and adapting it to transition metals. So a transition element is a D block element, and a transition element is something that forms at least one stable ion with a partially filled or incomplete D subshell. Okay, so that's a transition element. That's very important. Okay, so it must have an ion. Okay, that has it's a stable ion. There's a partially filled D subshell, not an atom, as you'll see later. So a D subshell can hold up to 10 electrons maximum. Okay, and for period 4 D block elements, only 8 of these are transition elements. So scandium and zinc, these are the ones which sit either side of that top row. So scandium is on the left and zinc's on the right. These are not actually transition elements. This is because when their stable ion that they form doesn't have a partially filled D subshell, so therefore it cannot be a transition element. But we'll look at more of that a little bit later in the next slide. Okay, so the electron configurations of the 8 transition elements in period 4, so we're going to look at them, and what we're going to see is you'll see they fill up singly first, then they double up, and this is because the electrons actually repel each other. I liken this a little bit to, say if you get on a bus, And so when you get on a bus, I normally find, I don't know, this is just something that I normally that I observe anyway, is that people would normally like their privacy and they'll sit on their own seat. So if somebody's sitting in one of the seats, they won't go and sit next to them. If there's an empty one, they'll go and sit in that empty one first. And it isn't until all of the seats are actually occupied, then if you want a seat, you're going to have to sit next to somebody else on the bus. So electrons are in a similar position in the fact that what they'll do is they'll kind of occupy their own orbital first, and then only when all the orbitals are full will it then have to then pair up. But this reason, it's repulsion, because they're negatively charged. So the two negatively charged electrons coming close to each other will actually repel each other. So you'll see how this works here. So what we're going to do is we're going to look at the electron configuration of some of these transition elements. Now, to make it a little bit easier, I've kind of put a little bit of a shortcut in here, and you'll see I've got AR in square brackets. And basically what this means is this is the electron configuration of argon. So all of these electron configurations I'm going to show you of the transition metals in the top row of the transition metal block, or the D block, then the instead of writing out the electron configuration all the time of the first few orbitals that you can see here, what we can do is we can just write AR. That's the transition. That's the noble gas configuration, and then whatever's changing here. So that's the noble gas configuration there. But you'll see what I mean. So titanium has the noble gas configuration. Has the noble gas configuration, plus it has 2 electrons in the 3D subshell and 2 in the 4s one. These two are very close in energy. That's why these are written here. Okay. Vanadium is the next one down, that has 3 electrons in the 3D and 4 and 2 in the 4s. Now it gets a little bit strange when it gets to chromium, and you'll see there's chromium. So what actually happens is that in order for this to form a half full 3D subshell, that's quite stable, that configuration. One of the electrons in the 4s actually jumps down into the 3D orbital here. Because these orbitals are very close in energy, they can the electrons can move, fairly readily between 3D and 4s. And so actually this configuration is more stable than having the 4 electrons on their own and 2 in there. So this is the most stable configuration. And then the next element is manganese. So manganese here, we put the electron back into the 4s orbital again here. Okay. The next one is going to be iron. So now you can see at this point we now have to pair up some of these electrons. So because there's no other space for them to go. So iron is that, and then we've got cobalt, which is that, and then we've got nickel, which is that one there. Now another one, here's another strange one. You can see now we have a position similar to chromium, where we have, if we add another electron in there, we can form a full 3D subshell, which is stable. But one of the electrons in the 4s has to jump into this orbital here. So that's effectively what happens with copper, which is there. So there's 2 things to watch out for here. You've got the copper and you've got the chromium electron configurations, which are slightly different. Okay, so that's the key thing that you've got to remember. They don't have the electron configuration. So for example, this is for chromium. Chromium doesn't have the electron configuration of that. Okay, where it's got 4s2, 3d4, it's 3d5, 4s1. So one of the electrons jumps into the 3d orbital because it's more stable. Okay, so just make sure you're fully aware of that, because that's a bit of a pitfall that they could pick you up on. Okay, so let's look at scandium and zinc. So remember I told you about these 2 elements in particular. So these are D block elements, but they're not transition elements. So we're just going to kind of dig into this a little bit more. Okay, so scandium only forms one stable ion, which is Sc3+. That's the only stable ion that it forms. So this has an empty D subshell. Okay, so we take 3 electrons away from scandium. So if you imagine it, the electron configuration, we take 1 from the 3D and the 2 4s ones, and that means you don't have any electrons at all in that 3D subshell. So because it's not partially filled, then there's your electron configuration. It's probably better for show you, isn't it, rather than just imagine it. So you can see there, that's the electron configuration for scandium element, but the ion, the only stable ion it forms is scandium 3+, and you can see that is empty, so it's not partially filled. So because the 3D subshell is not partially filled, that means scandium is not a transition element. And likewise, that goes with zinc as well. So zinc's at the other end of that row there. So zinc only forms one stable ion, which is zinc 2+. So Zinc 2 plus has a full D subshell, as it's not, so it has a full D subshell, so that means it's not a transition element. Now the reason why is if we look at our electrical configuration of zinc, it's full. So we've got 3D, a full 3D, and a full 4s. But actually, and we'll see this a little bit later on as well, when we remove electrons from an atom, we remove them from the 4s first, then the 3D. So the effect on zinc is it still has a full 3D subshell. The 4s one has no electrons in there whatsoever. Okay, so very important, when we're removing electrons, we remove them from the 4s first, then the 3D. Okay, so that's really, really important when we're looking at ions. And this is the reason why scandium and zinc are not transition elements, but they are D block elements. Okay, so let's look at this in a little bit more detail here. So what we've got is an electron configuration or electron diagram showing orbital energies. And you can see here, this shows it a little bit better where you've got 3D and 4s are kind of very similar in energy. Okay, the energy levels here are very similar. So the electrons can move quite readily between them. So what we're going to do here is we're going to look at how transition metals lose electrons, a little bit like what we've seen with zinc. This is just to confirm it. But if we look at the transition metal in particular for iron, so the electric configuration for one of iron's ion is Fe3+. And Fe3+ is formed by losing 3 electrons. And so the electrons are lost from the 4s first, so 2 electrons in the 4s, and then 1 from the 3D. So this is what we should have. So you can see here that we've got the electric configuration of iron, which is there. Now, if we remove 3 electrons, we end up with this configuration. There we are. Okay, so we end up with 3d5. Now that is a partially filled D subshell, so iron is a transition element. So that's fine. What you should always do is check. Okay, so use the smaller numbers on here. Tells you the number of electrons in this atom here. That's what the smaller numbers tell us. So using the smaller numbers, they should give us, so it's 26 is the number of electrons in iron atom. We're going to take 3 electrons away and we're going to have 23 that's left over. So add these smaller numbers up and they should add up to 23. So just make sure you've got that. Okay, so we lose from the 4s in terms of the diagram. There it is. And then we take it from the 3D. So that's the diagram for iron 3+. Okay, as long as you remember that, remove from the 4s first, you must empty that first, then the 3D. Okay, so that's when we're ionizing or removing electrons from it. Okay, so let's look at, so we've looked at the electron configuration, we've looked at the structure of, well, what's a transition metal and what's a D block element, so we can distinguish between that. So now what we're going to look at, we're going to really focus quite a lot in this video, understandably, on transition metals rather than just scandium and zinc. So what you need to know are the properties of transition metals. So transition metals actually have some quite unique properties, and this kind of whole module of developing metals, so the DM topic, is all about metals. So it's all going to be about transition metals and their reactions, or other metals and their reactions. So transition metals have specific properties which include they have variable oxidation states and they form coloured ions as well in solution. Okay, so we're going to look at quite a lot to do with colours, a lot of colour in this one. It's a nice topic. Okay, so transition metals have variable oxidation states, and this is because, remember what we said before, that 4s and 3D energy levels are actually really close to each other. Okay, now, as a result, the electrons are gained and lost using a similar amount of energy when they form the ions seen in the table to the right. So you can see here that we have various different ions are formed depending on the transition metals. So this is just some of them here. Obviously, remember, zinc and scandium, these are not transition elements. These are the only stable ions they form, but the rest are transition elements, as you can see in between there. Now, the ones that you need to know, thankfully you don't need to know all of them, the ones that you specifically need to know are the ones that are circled. Okay, so you need to be aware of the copper and the iron ones there. And in particular, you need to know the colours of these when they're dissolved in solution. So here they are. So you can see the coloured ions is iron 2+ is light green, so you need to know that Fe2+ is light green colour when it's dissolved in water. Fe3+ are like a yellowy, orangey colour when they're dissolved in water, and copper 2+ is blue. Now, the copper 1+, this is unstable. So copper plus is unstable in solution. And what will happen is this will readily disproportionate into Cu2 plus and copper readily. So although you do need to know about the copper plus, you do need to know that readily disproportionates, which means the oxidation, basically this element here is reduced and oxidized simultaneously. So you can see here it's been oxidized to form Cu2 plus, and it's been reduced to form Cu, as you can see there. So you can see that this one's unstable, so it disproportionates into these two species there. As long as you're aware of that, that's all you really need to know with copper plus. But you do need to know the colours of Fe2 plus, Fe3 plus, and Cu2 plus. Okay, so let's look at the complexes. So one of the features of transition elements is they're able to form complexes. Now complex sounds complex, doesn't it? It's not actually that bad. It's fairly straightforward. It's a common property of these, and it's a very useful one, as you're going to see later. We're going to look at what these complexes look like. But the ability to form complex ions is quite unique to transition elements. So a complex is basically, or complex ion is where we have a central transition metal ion, and it's surrounded by ligands bonded by dative covalent or coordinate bonds. Okay, so this middle bit here, there's your central metal ion in the middle, and this is what the complex looks like. The red arrows actually show dative covalent or coordinate bonds. And this is where electrons come from one species, in this case it will be the ligand, and they're donated to the central metal ion in the middle here. So that's quite unique in terms of they form this coordinate bond, this dative covalent bond. Okay, complexes as well, generally, not always, but they have a charge, as you can see on the top there. And they actually have a square bracket, and the square bracket basically shows the overall charge of the complex. Okay, so you can see here that we've got ligands here. These ligands may have a charge or they may not, depends on what that is. We'll look at ligands in a minute. And then the metal ion itself may have a charge. So if we basically add all these charges up, we get an overall charge of the complex. Now sometimes the overall charge might be nothing, in which case there isn't a charge there, so it doesn't always have to be one there. Okay, so complex ions can come in different shapes as well, but we'll look at the shapes of these complexes a little bit later on. So as long as you're aware of what a complex is, that's basically a complex. It's like a big molecule with a metal ion in the middle, and we've got ligands, and L stands for ligands, which go around, and actually that's what we're going to look at now, what these ligands are. Okay, so a ligand is basically just an ion, an atom, or a molecule that has at least one lone pair of electrons, and they can be monodentate, bidentate, or they can be polydentate, monodentate or unidentate. So they're the same thing. So monodentate, bidentate, or polydentate. Okay, so ligands have this unique, this very specific property, which must have a lone pair of electrons, because it's going to form a dative covalent or coordinate bond with that central metal ion. So ligands which only have one lone pair of electrons are called monodentate or unidentate ligands. So specific examples that you need to know are water, so H2O is a monodentate ligand, ammonia, which is NH3, as you can see there's NH3, Cn-, the cyanide ligand, and a chloride ligand. So these are all monodentate or unidentate ligands. Okay, so they only have one lone pair of electrons that is used to form a dative covalent bond with the metal ion. So ligands which have two lone pairs of electrons are called bidentate ligands. And the specific examples that you need to know are ethane diorate, as you can see there, it's just like a dicarboxylic acid, with a lone pair obviously on the oxygen. And we also have ethylene diamine, or also abbreviated to EN. So using EN is just a bit quicker than writing all that molecule out. Okay. So ligands which have more than two pairs of electrons are called polydentate ligands. So these are a classic example which you do need to know is EDTA. So EDTA 4- is an example of a polydentate ligand. It actually has 6 lone pair sites which it can bond onto that central metal ion in the middle. So it's quite a big ligand. It's massive. It literally surrounds that metal ion in the middle. So this is a polydentate ligand. Poly meaning bonds more than once. Okay, so multiple times poly. Okay, so now we know what a ligand is, we now need to attribute these ligands. Remember what we said about the shape as well. The shape of the complexes can change. But what we're going to do is look at these ligands and how do these ligands help to determine the shape of your complex. Okay, so let's look at complex shapes. So the shape is dependent on the size of the ligands and the coordination number as well. Now, what you can't get confused, you can't mix up coordination number and ligands. Okay, there's a big difference, but we'll look at them. So the coordination number is the number of coordinate bonds in a complex. It's not the number of ligands. Okay, so coordination number, coordinate bonds, number of coordinate bonds, not the number of ligands. So you might have, for example, EDTA can form 4 coordinate bonds. Okay, so it has a coordination number of 6, but we only have 1 ligand because EDTA is a large ligand. Okay, so let's have a look at the size of these ligands, because the size is important here. So some ligands are small, and small ligands, you can fit 6 of them around that central metal ion, such as water, ammonia, and cyanide. These are classed as small ligands. Okay, so you can fit a lot of them around there. So I'm going to use this analogy of a bit like pigs around a trough. So you've got a trough, and the trough is like the metal ion in the middle, and you've got the pigs, which then feed from the trough. Okay, this around the trough. Now, if you've got tiny or small pigs, then you can fit more of them around that trough, but the trough's a fixed size. Okay, so the baby pigs, or piglets, should I say, these actually, you can fit 6 of these around that trough, so they're classed as small ligands. So bigger ligand is chloride ligand, so the Cl- is bigger. Now, because it's bigger, we can only fit 4 of these round. So that's a little bit like bigger pigs. You can only fit 4 pigs around this trough because there's simply not enough space to fit them round. So chloride ligand, or Cl- is classed as a larger ligand, and you can only fit 4 of them around the metal ion. And finally, the other ones are your bidentate ligands, such as ethane diarate and ethylene diamine as well. These are larger again, as you can see, they're a bit more bulky, and normally we can only fit 3 of these around the central metal ion. So these are like fatter pigs trying to squeeze around this trough. We can only fit 3 of them around the metal ion. Okay, so that's important because the size of the ligand is now going to determine the shape of the complex that they form when we have them. Okay, so let's have a look. So complexes with a coordination number of 6, these form octahedral shapes. Okay, so for example, we've got a cobalt metal ion in the middle here, and we've got a small ligand, this is water, surrounding the cobalt ion in the middle. And this can also be written as this. And you're going to see this quite a lot when we look at some of the equations later on, where we write the transition metal, which is cobalt, and then in square brackets, we then put the ligands that are surrounding it. So in this case, it's going to be 6 water ligands surrounding this. So this is just cobalt put into solution. Okay, the overall charge is 2+ on here. Okay, so we can work this out. Actually, we'll quickly go through this. We can actually work this out by water has a neutral, has no charge. We know that water doesn't have any charge. So we've got 6 of these. You can have as many waters as you like, and that's not actually going to change the overall charge. So this charge is actually coming from the charge of the metal ion in the middle. So that must be 2+ in the middle there. So let's have a look at another example. This is ammonia, and we know ammonia is a small ligand as well, a bit like water. So we can fit 6 of them around the cobalt in the middle there, and clearly that can also be written like that. Okay, so very similar to the water one, as you can see. Now, these are octahedral. Now, you may remember from year 1 chemistry, and when we looked at shapes of molecules, octahedral shapes have a bond angle of 90 degrees between each of them. No different from what you've seen in year 1 chemistry. We're just applying this to transition metal complexes instead. So that's an octahedral shape. So we've got 6 of them around there. So complexes with a coordination number of 4 form tetrahedral and square planar shapes. Okay, so let's have a look at this one. So here's an example here. This is copper with 4 chlorine ligands surrounded it. So remember, chlorine is a bigger ligand, so you can only fit 4 of these around the central metal ion. Now, notice the charge on here, just to kind of, it's also written as this as well, but just to kind of go through the charges, then chlorine, we know Cl is Cl-. Now we have 4 of these Cl- there, so that's 4-. Overall, the charge in the complex is 2-, so that means that this must be +2. So that's Cu2+, that is a 2+ charge in the middle there. Okay. Now, because this is tetrahedral, The bond angle in tetrahedral is 109.5. Again, that's something you would have picked up on in year 1 chemistry, looking at the bond angle of tetrahedral complexes. So another one which you will have come across is square planar. Now there's a specific example you do need to know, which is this one here. So this is platinum with 2 ammonia ligands coming at the bottom here and 2 chlorine ligands. Don't worry, always default to tetrahedral unless they state otherwise, or unless it's this, which is also known as cisplatin. Okay, so cisplatin is an anti-cancer drug. So this is a specific example that you need to know, and you need to know that this cisplatin is square planar. You are expected to know that. Okay, so this is platinum with 2 chlorine ligands at the top and 2 ammonia ligands towards the bottom there. Now you'll know from year 1 chemistry that the bond angle in square planar complexes are 90 degrees. Okay, so you have this flat shape there. They're a flat complex, and you'll notice with anything to do with 3D diagrams, we have wedges and we have dotted lines. The wedges show bonds coming towards you, the dotted lines showing going away. Okay, but they're all coordinate bonds. That's the key feature of these complexes. Okay, so now we know about these complex shapes. We know they can form these large complex structures, and we know about ligands, and we know about the metal lines in the middle and the overall charges and how we work that out. One of the key features as well of transition metals, as we've said, transition metals, is colour. Okay, and we need to understand how do ligands, or the type of ligands, affect the colour of what we see. Okay, so this is all down to something called d orbital splitting. Okay, the D subshell is split into 2 when ligands bond with the central metal ions. Remember, we looked back at the electron configuration. We'd seen we had the d orbitals, the 3d orbital, the 4s orbital. So we just shown you before, the orbital is actually just in a row. It's linear. What actually happens is when we bond a ligand to that transition metal, the d orbital actually splits. So this is the linear configuration that you've seen before. So this one's cobalt 2+. So this is just hypothetically, this is saying that that we have no ligands attached. Then the d orbital is actually in a nice, neat, linear arrangement like this. So there's no splitting of that d orbital. But the moment we add a ligand to it, something weird happens here. And what happens is the d orbital actually splits into 2, as you can see there. So you can see here we attach some ligands, and some of the orbitals gain a little bit more energy, so they're a little bit higher up, as you can see there, than these orbitals here. And we create an energy gap, which is delta E, which is this bit here. Okay, so for example, cobalt dissolved in water to form your cobalt hexa-aqua complex, which is this one here. Okay, so we get this splitting of it. Now this is called a ground state. So in other words, we've got some of the electrons here go to the top, and 3 of them are at the bottom, which is here. Okay, so this is the ground state. I'm going to come on to what we mean by ground and excited state. We'll look at that in a moment. Okay, so when electrons absorb light energy, some of them move from the lowest energy level, the ground state, which is this configuration here in the yellow box, that's all of that, to a higher energy level state called an excited state. So let's have a look at what we mean. So there it is. So there's your excited state. So you can see here that what's happened is in the ground state, we've had 2, 2, and 1 in the bottom here. But when we give it a little bit of energy, so that could be light energy, for example, then this electron absorbs some of that energy and it jumps up into the higher energy orbital, as you can see there. So we now have 2, 1, 1 at the bottom. So this is the excited state. So in order for this to happen, the energy from the light that we're introducing to this complex, that might be visible light, for example, is a really classic example. That visible light has energy, but the light must equal delta E, which is that energy gap. Okay. Now that gap is dependent on some certain things. So the central metal ion and its oxidation state. So depending on the metal ion in the middle will depend on what that energy gap is going to be, that delta E. Also, the type of ligand can affect the size of that gap as well. And the coordination number can also affect the size of the gap. So, for example, if it's got 4 ligands or 6 ligands, or 6 coordinate bonds, or 4 coordinate bonds, or or if it's only got, well, you can get linear as well. You don't really need to know about linear, but you can have 2 coordinate bonds as well. So these are the things, there's 3 things which affect the size of that energy gap. And as you'll see on the next slide, the energy gap actually gives, or this feature allows transition metals to have various different colours. So it's brilliant. I love this type of chemistry because it's all nice and colourful. Okay, so this leads us on nicely onto coloured complexes. Okay, so some frequencies of visible light are absorbed by the transition metal. So imagine you had a test tube with some of this solution in. Okay, so we know it's a coloured solution. If you've done this already in the lab, in school or in college, you'll know what I mean. But if you haven't, then these complexes, transition metal complexes, are coloured. In when you dissolve them in solution, or if you add hydroxide to it or ammonium. We're going to have a look at them later. But what happens is some of the frequencies of visible light are absorbed by the transition metal complexes, and the frequencies absorbed depends on the size of delta E. And so remember, we know what affects delta E because we looked at that before. Okay, so we know there's 3 things that affect that. So basically, the larger the energy gap, or delta E, the higher the frequency of light that is absorbed. Now, if you do physics, this might be quite straightforward, but basically this is the spectrum of white light. So if we split white light, we get these colours here. And your indigo and violet colours at the top here, these have the highest frequency, and your red down at this end has the lowest frequency. So the larger that delta E, that gap that we'd seen on the previous slide, the higher the frequency of light is absorbed. So this is what's absorbed by the complex, okay? Very, very important. Okay, so any frequencies which are not absorbed, okay, so in other words, if we had a very large energy gap, let's say, and we have the violet was absorbed, then all of the rest of the colours here, these will either be reflected or transmitted. So all the rest of these colours would be reflected out of the test tube, okay? So the combination of all of these frequencies that's left behind create a complementary colour that we observe with some of these complexes. Okay, so for example, if let's have a look here. So we've got copper 2 plus solution. So we know that this absorbs frequencies that produce red light. Okay, the complementary color is light blue or cyan. So basically, if we have copper 2 plus solution, you might have seen this before, copper 2 plus solution or copper sulfate, for example. So you add copper sulfate to water and you form this complex here. Now that complex, when white light is shining against that test tube, it's actually absorbing red light. So it's absorbing red, but obviously it's not red. We're not seeing it as red, but it's absorbing this frequency here, and it's the blend of all the remaining colours here. If we blend all them together, that gives us cyan. That gives us this blue colour. So this is what we call a complementary colour. So depending on what's absorbed will depend on what we see. So what's absorbed is not what we see. Okay, what we see is the combination of the remaining colours that aren't absorbed. I hope you get what I'm saying. Okay, so excuse me. So it's quite complicated, as you can see. Okay, so for those complexes where we have a full or empty 3D subshell, then no electrons can actually migrate to the higher energy level. And this means we see these as colourless or white. So these are things like scandium and zinc are classic examples. So these are not transition elements. Remember, they have full 3D subshell, which is zinc, or scandium has none at all. So because it's full, we can't actually move any electrons up or down. When we split them orbitals, they can't move anywhere. So because they can't move anywhere, we don't get any colour from them. And likewise with scandium, they don't have any electrons to move. So this is why these two do not form these coloured complexes, because there's no space for them to actually move. So it kind of makes sense, doesn't it? It's all kind of coming together. I hope so anyway. Right, okay, so we know about colour complexes. We're going to come on to this a little bit later on as well, towards the end of this video, when we look at analysis of transition metals and trying to identify them. We can use these features here. Okay, so what we're going to do, so we know about coloured complexes, and we know what can affect colour. So it's about the shape of the shape can change the colour. The oxidation state of the metal ion in the middle can change the colour as well as the different type of metal, and also the type of ligand can change the colour. So what we're going to do is we're now going to look at a specific set of reactions here, and we're going to look at these colours and what's actually happening. So when we react the aqueous metalline solutions with aqueous sodium hydroxide, which is NaOH, or aqueous ammonia, then we form metal hydroxide precipitates. Okay, so we form these different colours. So what we're going to do is we're going to go through, and these are the ones that you specifically need to know. So remember, in the previous slide, we said you need to know copper 2+, iron 2+, and iron 3+. You need to know all the reactions here and the colours associated with them as well. Okay, so you've got to be vigilant. So spend a bit of time trying to remember all this, because it's going to get you a lot of marks in the exam. Okay. So just before we look at the different parts here, metalines dissolved in water only have this formula, remember. So it's this hexa-aqua complex. So when we take our metaline and we add it into water, such as copper sulfate, for example, we add that to water, it actually forms this hexa-aqua complex. So what we can do is we can simplify this to Mn+. Okay, that just means that means exactly the same as 6 water ligands. Okay, so just make sure that you're kind of familiar with these two terminologies. Really, when you're writing your equations, you should be writing it like this. Okay, because that shows the examiner that you know exactly what you've actually got here. Okay. Okay, so let's look at the copper one first. So when we add copper, let's say copper sulfate, and we add that to water, then we form our copper hexa-aqua complex, as you can see there, or copper 2+, aqueous, okay? And this is a blue solution. So remember, that's that kind of pale blue colour that you would have seen. Now, if we add some sodium hydroxide to it, or ammonia, to this solution, we're actually changing the ligands here, so we get a colour change. So let's have a look. So here we get a paler blue colour. So instead of this blue solution, we get a paler blue colour, but we also get a precipitate. Now what's really important here is you can see we've got CuH2O6 2+. We're going to add a small amount, not loads, just a small amount of hydroxide. So that's going to be 2OH-, and this is going to form this complex here plus water. Now the reason why we form a precipitate with either of them is because the complex is now neutral. So it doesn't have a charge. Notice none of these, whether it's ammonia or hydroxide, has a charge. Now because it doesn't have a charge, that means it'll form a precipitate. You'll form a solid, so it precipitates out, as you can see there. Okay, so this is a blue or pale blue precipitate, is obviously formed here. The reason why this is neutral is effectively we've got a neutral ligand here, and the copper here has a 2+ charge, because that's what it says on there. And we're adding two negatively charged, there's two negatively charged OH- that have been formed within the complex here. So these have a 2 negative charge, so negative each, and these are neutral. So if we've got 4 neutrals, 2 negatives, and a 2+, which is the copper, then we get a neutral complex. And anything that's neutral or has no charge will precipitate out, as you can see there. Okay, so that's why we need 2 OHs, 2 OH-, and 2 ammonias to form this neutral complex there. Now, if we add excess hydroxide, so we've added that, we're going to keep on adding hydroxide, then we get an insoluble substance. So, well, a substance is insoluble, so it doesn't disappear. Okay, so it's you still have that precipitate. Okay, so it's insoluble in excess sodium hydroxide. But if we add excess ammonia to the precipitate, then what we get with copper, it's a bit of a strange one, we get a partial ligand substitution. So you can see here, there's our copper hexa-aqua complex. We're adding excess ammonia, so more than the 2 that we had here. And what we get is we get a ligand substitution. So basically 4 of the water ligands are substituted for 4 ammonias, as you can see there. 2 of the water ligands remain. These bonds are fairly strong, so that they can't be substituted by the ammonia. But notice that we've now got a neutral and a neutral, so that hasn't changed because ammonia is neutral, remember, as well. So this is still charged, and therefore it's aqueous. Okay, so it's still aqueous here, and obviously the 4 waters have been kicked off as well. So that's a partial ligand substitution, so just be careful with that one. Okay, so looking at iron 2, so iron 2 is a pale green colour. Okay, same principle applies to copper. So when we add some hydroxide or OH- and some ammonia, we have the same principle that happens. We form a solid complex here, so this is the precipitate because it's neutral, and we form the same product as you can see on there, so there's no difference there. The colour's clearly different. From pale green we get a dirty green precipitate that's formed there. And then when we add excess hydroxide to that precipitate, it's insoluble, so that's quite easy. And actually when we add excess ammonia to iron 2, that's also insoluble in excess ammonia, so there's no change there. Okay, so finally Fe3+, so this is a yellow colour, as you can see there. This is when we add it to an aqueous solution. Now when we add some OH- or some ammonia, there's a subtle difference here in the fact that we need 3 OH- to form this neutral complex here, because we had a 3+ charge. You see, so we need 3 of them to form a neutral complex there. Likewise with the ammonia as well. So these are neutral complexes, so they form a solid. Now the precipitate is orange in this case for this one there. Again, when we add excess hydroxide, we get it's insoluble, so there's no change, and it's also insoluble in excess ammonia as well. So that makes it nice and easy, doesn't it? So the only one where you get a change is the copper one when we add excess ammonia to that. Okay, so let's carry on and look at some other transition metal complexes as well. And we looked at it a little bit there in that table about ligands being exchanged, particularly when we added excess ammonia to your copper 2 plus aqueous solution. Now this is called ligand substitution, as I said, so it normally leads to a colour change when we're substituting. We're changing one ligand for another, okay, so we get a substitution reaction. So here is an example of ligand substitution where the coordination number is the same, and so the shape is the same as well. But you can see here that we have chromium in this case with 6 water ligands surrounding it. We add 6 ammonias in this case, and we're going to get a complete ligand substitution here. So all the water ligands are being substituted for ammonia, and we get our 6 water ligands that are removed. So looking at the colours here, so it's dark green on the left, but the shape is octahedral. Now it's still octahedral on this side, but the colours change to purple, and this is because we have a different ligand attached to it, and therefore the delta E, that gap between the d orbitals that have been split, changes, and that's why we get a different colour, okay, because the ligand has an impact on that. And so here's an example of ligand substitution where the coordination number changes and so does the shape. So this normally happens when we have a smaller ligand like water or ammonia or OH-, and that's exchanged for a bigger ligand like chloride, like Cl-. So let's have a look at an example here. So we've got copper hexaaqua here. We're going to add chloride ions. That could be hydrochloric acid, for example, will give us this. So Cl- ions, and then we're going to form copper chloride, CuCl4, 2-, plus your 6 waters as well. So the colour here is pale blue, and it's octahedral on the left. And here we've changed the shape this time with this one. So we've now got a tetrahedral structure, and so the colour changes to yellow because the shape has an impact as well on the colour. Okay, so now we're going to look at catalysts. Okay, so catalysis is another feature of transition metals. Transition metals are really good catalysts, and we need to understand how a catalyst works. So remember from last time, or earlier on in the video, that we said that transition metals have variable oxidation states, and we looked at that table with all the different oxidation states on them. That feature allows them to be good catalysts, and the reason why they're good catalysts is it allows them to receive and lose electrons, and that allows in the substances that we're reacting, and that speeds up the rate of reaction. Okay, so that's what a catalyst does. So you can see in the manufacture of sulfuric acid, so this is the contact process. So we make sulfuric acid, which is a bulk chemical used in loads of different chemical reactions. So it's a vital reaction. But in the manufacture of that, we use vanadium compounds. So we use V2O5 as a catalyst, and it's used to catalyze SO2 to SO3. And then what we do with that SO3 is we bubble that through water and we form sulfuric acid. So we're just looking at one of the steps in the manufacture of sulfuric acid. So the first step is that we use the V2O5 oxidizes the sulfur dioxide to SO3, but itself V2O5 is reduced to V2O4. So the reaction is this. So it's V2O5 plus SO2, sulfur dioxide, will form V2O4 plus SO3. So that's the first step. And then what happens secondly, because it's a catalyst that has to be reformed, then the V2O4 is actually oxidized and it reforms V2O5. Remember, catalyst is never used. It always has to be reformed. So the V2O4 reacts with oxygen to form V2O5, and then that's then allowed to react further and continue. So very important, and they're actually used, like I say, to make the product faster. This means we can lower the temperature of the reaction, and that saves energy, it saves money, and it helps the environment, because normally the heat that we need for reactions to occur is normally generated through the burning of fossil fuels. So if we don't have to use as much heat, then we're not burning as much fossil fuels, and that's got to be better for the environment as a result. Okay, but we've got to be careful with catalysts. Catalysts are good at speeding up reactions, but there are hazards associated with transition metals being used as catalysts. So examples for some of them here are copper. Copper actually forms or has chronic exposure, can cause damage to the liver. You can get liver damage by exposure to copper long term. So the copper catalysts. You can get a ring of copper in the eye, shows that someone's suffering from copper poisoning. So you can see in the picture here, you've got this just around the eye. I hope you can see it quite relatively easy. It's quite subtle, but you'd see we've got this copper ring around the eye there. Another example of a catalyst is manganese. Now, long-term exposure to manganese catalysts can cause psychiatric issues, and you can get tremors as well. So not exactly the type of stuff you want to be exposed to a long period of time. So you have to have suitable PPE when you're handling some of these transition metal catalysts. Okay, so let's look at some of the types of catalysts that are available to us. So catalysts can be homogeneous or they can be heterogeneous. So let's look at heterogeneous first. So hetero means different. Okay, so this is a catalyst that's in a different phase from the reactants. Okay, so the catalysts in a different state to the reactants. So our a classic example being the Haber process. So this is the manufacture of ammonia, which is used in agriculture as a fertilizer. So a very important process. But the catalyst we use here is an iron catalyst. Now irons are solid, but our reactants and products are gases. So you can see here that it is in a different state to the actual reactants and products here, which are in gas phase. So to try and improve the performance of the catalyst, then if we increase the surface area of the catalyst, of heterogeneous catalyst, this will actually increase the rate of reaction. So for example, we take that iron and we grind it into a fine powder, we increase the surface area, and this means that more particles can actually react with the catalyst at the same time if we've got a larger surface area. So that improves the performance of heterogeneous catalysts. There are homogeneous catalysts as well, so this means they're in the same phase as the reactants. So homogeneous catalysts are normally in aqueous solution, so it's normally with aqueous reactions and an aqueous catalyst. So for example, we're using sulfuric acid to make an ester, is a classic example of this. Now homogeneous catalysts actually have a slightly different energy profile. They actually form an intermediate species by reactants combining with the catalyst, which then react to form the products, and then the catalyst is then reformed back again. So the homogeneous catalysts actually integrate quite integral within the reaction, whereas a heterogeneous catalyst just kind of sits on a plate and the product passes through the powder, let's say, whereas a homogeneous catalyst is actually integral within the reaction. Excuse me. Right, I'm starting to lose my voice, I think. Right. So let's look at a little bit more detail at heterogeneous catalysts. So heterogeneous catalysts work by substances adsorbing, that's not a mistake here, that's definitely a D, adsorbing to the surface of the catalyst. So reactions occur on solid heterogeneous catalysts, so they actually occur on the surface of these, and like I say, the substances bond or adsorb to the surface of the catalyst, and that allows reactions to happen. So the reaction actually happens on the surface of these catalysts. So bonds in the reactants weaken and break to form radicals, which are basically atoms or molecules with an unpaired electron. So for example, Cl radicals, or chlorine atom, and these radicals react with each other to make new substances. Okay, so this is basically how heterogeneous catalyst works. And so these new molecules are then released from the surface of the catalyst, and we call that desorption. So the reaction happens on the catalyst surface. Okay, so let's bring back that other example that we mentioned before. So this is the manufacture of ammonia, so in the Haber process. So we're using an iron catalyst in this reaction. So here's our iron catalyst surface here, and we've got adsorption of the substances. So here they are. So there's your adsorption. So you can see, there you go, we've got our hydrogen molecules and our nitrogen molecules. So this is adsorption, so they stick to the iron catalyst. That allows the reaction to happen. Once the reaction has occurred, we then get desorption, they break away, as you can see there, okay, and that's basically how the reaction works. Okay, so you've got adsorption and desorption, so make sure you're aware of that. So a good catalyst will attract and hold the reactants long enough for a reaction. If they don't, then the catalyst isn't very good. A good catalyst as well will not attract products too strongly, otherwise desorption won't occur either. So you need enough of an attraction, just enough for that reaction to happen. So it's a very fine balance, as you can see. Okay, so copper and manganese are other examples of transition metal catalysts, as we've seen earlier. We've got to be careful with these types of catalysts. But copper, so solid copper sulfate is used to catalyze reactions of acids reacting with zinc, for example. So we use copper sulfate as our reaction there. So you need to know this particular example. These are specific examples that the exam board want you to know. Okay, so zinc reacts with sulfuric acid to form zinc sulfate, and hydrogen. Obviously, we use the catalyst solid copper sulfate to catalyze that reaction. And manganese, solid manganese dioxide, or MnO2, is used to catalyze the decomposition of hydrogen peroxide. So we need to know that hydrogen peroxide breaks down into water and oxygen. Okay, so you need to know them specific examples there, and obviously you need to know the risks as well associated with handling copper, as we said before, and handling manganese as a catalyst. Okay, so let's look at homogeneous catalysts, because remember we've got these types of catalysts as well as heterogeneous. So homogeneous catalysts, these combine with the reactants to form an intermediate. So it's not like heterogeneous where you have a surface and the substances adsorb to the surface and desorb. These actually form an integral part of the actual solution that we're reacting. They form an intermediate, but just like with any catalyst, it must remain unchanged at the end of the reaction. So in this case, they're reformed. Okay, so a catalyst always, this is any catalyst, whether it's homogeneous or heterogeneous, it lowers the activation energy. So this means less energy is required to allow the reaction to happen. So this is the main part of a catalyst. So remember, the catalyst is always reformed. It's never actually used up. It's really important. So let's look at this particular example here. Now you need to know this example, specific one as a homogeneous catalyst. So oxidation of iodide ions using peroxide disulfate, which is S2O82-, as a catalyst. Okay, so this is a homogeneous catalyst. It's a little bit more complicated, but there's a rationale behind this. So the reaction uncatalyzed is really slow. So we can see here what we're trying to do is react this, which is a 2-, with this, which is a minus. These two negatives are never going to react with each other. I mean, they're just, unless you give them really severe conditions, these are just going to repel each other. So we need something that allows these two react, but we need something to kind of act as a mediator, I suppose, between the two, or a catalyst. Okay, so these two here are never going to react, so we need a catalyst to react here. So it happens in 2 steps. So step 1, we use the Fe2+ as a catalyst in this example here. Okay, Fe2+ is a solution, so it's all in the same phase. It's a homogeneous catalyst, and this lowers the activation energy. It speeds up the reaction. So the first step here is the peroxide disulfate S2O82- reacts with. Whoops, let me just go back. Previous, there we go. Okay, so you can see here we've got S2O82- reacting with 2 Fe2+, as you can see there. So these will react because that's a negative and a positive, so that's fine. And what happens is the iron is oxidized to Fe3+, and the S2O82- is reduced to SO4 2-. Okay, so we've got 2 lots of that. So there's one of our products, look, there. Okay, so then what we need to do is this Fe3+ that we formed, always we must have Fe2+ as a product, okay, because it's a catalyst, so it must be reformed. So the second step is that Fe3+ intermediate produced in that first step reacts with the I- ions, that's the other reactant that we need here, and that forms iodine, I2, and obviously we reform our catalyst back again. So that's Fe2+, as you can see on there. So you can see this is a homogeneous setup. You form an intermediate, and it's crucial that the catalyst is reformed as a product in that second step there. Okay? Right. Okay, so we're now going to move on to the last section of this video, which is looking at colorimetry. And colorimetry is a really useful technique of trying to identify our transition metals. Okay, and obviously we're using color. And the reason why we're using color is because we know that one of the main features of transition metals is they form colored complexes. Okay, and we've looked at that with the d orbital splitting. So remember, the colors that we observe are complements of the ones of the colors that are absorbed by the actual transition metal. So remember, your white light is made up of all these colors here, okay? And so when that white light hits a transition metal, only one frequency, one of these in the spectrum, is actually absorbed. So if you remember that from what we said before, so any frequencies which are not, these are reflected or transmitted. So if you remember that, okay? So that means anything that is not here. So for example, if red is absorbed here, then all the other colors here blend together to reflect or transmit from the test tube. So the combination of all of these, they create complementary color that we observe. Remember that from what we mentioned before. And if we mix the complementary color and the absorbed color, we get white light. In other words, if we mix all these together, the absorbed and the complementary ones, then we get white light that combines. So if we bring back our wheel again, so remember the color wheel allows us to predict the color of light that's absorbed, and the one that's directly opposite is the one that's actually been absorbed. So for example, a green color, if we see green color, it means that magenta is being absorbed by the transition metal complex. So remember, what actually changes, or the color that is dependent on, is the type of the ligand, the shape of the ligand, so the shape of the complex, should I say, not the shape of the ligand. So the type of ligand, the shape of the complex, and also the oxidation state of the central metal ion. So these things impact the color that we see. Now, in terms of colorimetry, is a spectral technique. So this obviously, this setup here is a way in which we can identify certain transition metals. Okay, so colorimetry is used to measure the concentration of transition metal ions in solution. So it's got this setup here, okay? So a colorimeter measures the absorbance of light by a colored sample, and the more concentrated a sample is, the darker its color, and hence the more light is absorbed. So you can see here we've got this setup. We're going to use this diagram in a moment to show you what happens. So the first thing is the colorimeter, that's not calorimeter, that should be colorimeter, okay? So the colorimeter must be set to 0, and to do this, we measure the absorbance of a blank sample, okay? So the blank sample is normally the solvent we're using to dissolve a transition metal ion in, so that might be water, for example. So we shine the light through, and we take a 0, so we know that any absorbance has got to be because of the substance, the transition metal, rather than the solvent. Okay, so that allows us to do that. So once we've got that, once we've got our benchmark, our 0, then white light is filtered into a narrower range of frequencies. So we call this monochromatic light, or it's a single color is produced. So we've got white light there, it gets passed through a filter, and we get one frequency of light that is produced. Okay. Now the choice of filter here is really, really important. So the color produced from the filter must be absorbed by the metal ion solution. Okay, so depending on what filter we're using here, if we use the wrong filter, then it may not be absorbed at this end here. So we've got to make sure we're choosing the right filter here for the substance that we're testing. So once it goes through the filter, we get this monochromatic light, as you can see here. Now that's the coloured sample there. In reality, it looks something like this. This is called a cuvette, and you might have seen these. They've got a frosted side at two sides, and that's where you pick it up. And it's got a colourless side on the other side, and that's where the light goes through that cuvette. So you'd put your sample in there, and the light would then shoot through that cuvette, and basically we're measuring the absorbance of that light. So some of that light here is going through, will be absorbed by that coloured sample, and then at the other end, the light will go through the sample and it will hit the detector. Now what the detector is doing is it's measuring the difference between the intensity of light here compared to the intensity of light here, and it's measuring the absorbance, how much light has been absorbed by this coloured sample. Okay, so that goes through to the detector, and that's effectively what the detector is measuring here. Okay, so we use a calibration graph to measure the concentration of a transition metal solution. Okay, so this is what we're going to be using to see how much of that transition metal we've got in our solution. So first of all, what we have to do is we plot a calibration graph. So this is created by making up a range of known different concentrations of the transition metal solution. Okay, so and the absorption is measured for each one, and the results are plotted. So we use that bit of equipment that we've just seen before. So we take, say if it's copper sulfate solution, we make known concentrations of copper sulfate solution, we measure the absorbance of each of them concentrations, and we measure it and we plot it on a graph like this. So this is your calibration curve. So we've got absorbance against the concentration of a metal ion, which we've made up. We've deliberately fixed the concentrations of these so we know what the absorbance is of each. Now, we do this, we make the samples by diluting different concentrations of the metal ion, like I say, and we must use the same metal ion and the solvent to the one that's going to be tested. So in other words, if we're wanting to work out the concentration of a copper sulfate solution, for example, in other words, what's the concentration of copper ions in there, then we must make known concentrations of the same metal ion using the same solvent. So for dissolving it in water, we must use everything the same. Okay, and we use pipettes to measure the volumes of these known samples that we're making up here. We use a pipette to do that. Okay, so we then test the sample that we want to know. So we've got our known samples here. So we've made up a range of different concentrations, measured the absorbance, and plotted them on this graph. We then bring in our one that we want to test. Okay, and we measure the absorbance of that. Okay, so we put that into our colorimeter as it's shown before, and we measure the absorbance. And once we know the absorbance of that, we then plot it on this graph. And then this graph allows us to work out the concentration of the metal ion from the absorbance of our unknown substance. Okay, so we use that to work that out. So it's fairly straightforward, as you can see. It's a quite clever way of working out, the concentration of our transition metal ion. Now, finally, another way of using colour, we can actually identify transition metals as well in our solution by using something called visible spectroscopy. So it's also another way of measuring the concentration of transition metal ions as well. And we use monochromatic light, as we've seen before. But this time we're going to use a visible spectrophotometer. Okay, sounds complicated, doesn't it? So we're going to use one of them instead. So white light can be split into monochromatic light beams using a filter. So remember, we'd seen that before in the previous bit of equipment, so there's no change there. Okay, that monochromatic light beam is then passed through your sample, and the intensity is measured before it goes into the solution and afterwards, and this tells us the absorbance. Again, there's no difference to what we've just seen before. It's exactly the same method so far. Okay, so we then use the calibration curve and the absorbance, or the calibration graph and the absorbance, to find out the concentration of the metal ion in the solution. Okay, so that's what we've just seen in the previous slide there. Now with this one, what we can do is we can repeat that with different frequencies of monochromatic light. So we just keep repeating that same experiment, but we change the frequency of that. And this produces what we call a visible absorption spectrum. So we form something like this. So you can see there's our different wavelengths of visible light that we're putting in. This is the visible region, as you can see there. So that's the coloured light there. Okay, and any peaks that we see in here, as you can see there, this will tell us which colours the complex actually absorbs. So in this case, you can see here that this complex is absorbing in the green area. So the colours that we see is a combination of these colours here and these colours here. So we blend them together, and that's the colour that we observe. Now, complexes absorb different frequencies, and a characteristic spectrum is produced that allows us to identify that complex. So this visible spectroscopy is really useful, obviously, for measuring the concentration, just as we've seen before, but also we can identify our complex too. Okay, and a calibration curve allows us to convert the absorbance into the concentration data as we'd seen before. Okay, and that's it. So that's everything to do with the inorganic chemistry and the periodic table section of the developing metals topic. Like I say, there's 2 videos for this topic, so there is another one within the developing metals topic. So just have a look on Allery Chemistry YouTube channel. There's a full range of year 1 and year 2 videos on there, and there's also some whiteboard tutorials. They're all for free. All I ask is you hit the subscribe button. That'll be absolutely fantastic. And remember, if you want to get a copy of these for yourself, great value for money, click on the link in the description box. You'll be able to download them from there. You can use them on the move, smartphone, tablet, and I'd like to say I've known people print them off as well. Great for your notes as well. But that's it. Bye bye.